Hi guys, how you going? I'm just doing a bit of limits today, finding limits in a nutshell. That means I'm not going to go too deeply into we're not doing it rigorously. It's more like a hand wave version, talking about it, understanding what the limits are, and a bit of a quick contents table here. First, we'll look at the limit as x goes to infinity of 1 over x, and also minus infinity. And then we'll look at a limit at a point, at the limit as x approaches 3 of some function. And we're going to look at a few different functions. There's 1, 2, 3 functions there. And then also this one as well, number 5, that's where you have to do a bit of work. That one's actually undefined, but it can be made to work. And this one is a piecemeal function, and then I focus on that last one there. So let's have a look at these. I did 4 of them on one sort of page because they're kind of relevant. So these here. So let's look at these. Firstly, f of x is 1 on x. So that's a hyperbola. Parabola. And just get a red pen here. Let's circle the asymptotic bits here. Here, at this side of the function, what's happening is that as x approaches infinity, positive infinity, so infinity is on that side of the x-axis, minus infinity is on that side. You think of infinity as a very large number, like 1 million. As x approaches infinity, then y is actually becoming 0, isn't it? It's asymptotic there, and it's getting 0 from above. So we put a little plus on it. That can be helpful sometimes. So y approaches 0 from above. Similarly, on this side, as x approaches negative infinity, y approaches 0 again, but this time from below. So maybe I'll use a black pen for that. You can say that the limit as x approaches infinity of 1 over x, it's equal to 0. I like to write 0 plus because it helps me with the graphs to draw them. Sometimes you get a limit like this and you know it's approaching from above. You know the graph goes asymptotic and you know it does that above behavior. It goes down to the limit from above, so you know how it looks. It was really helpful. Also, the limit as x approaches negative infinity of 1 on x is, so for this one, you could say, okay, it's 1 on infinity, infinity algebra I call this, which is 0 plus. This one is negative 1 on infinity, so that's 0 still, but from the negative side. So this one's a positive number. This one is a negative number. This one, for example, think of it as 0.3, put 6 zeros in there or something like that, for example. Lots of zeros. And think of this one as being negative that. Okay, 2 secs. I'm going to turn that TV in the background off. Okay, I'm back. Now, and that's really the size of that. So the left and right limits, we're not talking about left and right limits, are you? So we've got two limits there. So the limit is 0 for both of those. That's their asymptotic. So that's example number 1. Example number 2, we want to find the limit as x approaches 3. So the left and right limits here are important. Let's talk about left and right limits. Look at the graph. The graphs are really important for this topic. If you can draw a graph, do it. As x approaches 3 from the left, this function is approaching 4 from the left, or from below in this case. And as x approaches 3 from above, the function is approaching 4 from above. So we can write all that down in the language of limits. So the limit, the left limit, the limit as x approaches 3 from the left. I find it helpful to write the words for some people can look back on it, of f of x, I guess it is f of x. And in this case, you can just substitute the f of x because you know there's only one f of x. This is x plus 1 for all x. And that's just equal to 4. Similarly, the limit as x approaches 3 from above, ooh, that was bad, let me rewrite that, of f of x. There's a lot of notation with this sort of stuff. It pays to play the game though. So that's 4. And in this case, the function also exists there. You can see that. So you've got the left and right limits are equal. This one's the right limit. Did I, yeah, I'd write that. So that's the, did I define that up there? This one is the left limit. And this one is the right limit. Okay. So the left and the right limits are equal. So therefore the limit exists. Well, the limit as x approaches 3 exists. The left and right limits have to be equal. And you write the limit as x approaches 3 of f of x in this case, which is x plus 1. Is 4. And that's all there is to that. Now, the other thing is that f of 3 is actually equal to 4 as well. So for this particular example here, f of 3 actually equals the limit as x approaches 3, which is important for continuity. So that means it's continuous there. But that's a bit extra that. But it's important for continuity. If the function is continuous at a point, then the left and right limits are equal, the limit exists, and the limit is equal to the function value there. All right, for this one here, f of x equals x plus 1, but x equals not 3. So 3 is not in the domain, so it's a line with a hole in it, with a point missing. I think of it as a hole. It's just a metaphor. In this case, in a nutshell, the left and right limits still exist. Well, I've drawn them in there. As you approach 3 from below, it goes to 4, and if you approach 3 from above, it goes to 4, but from above. So the left and right limits exist. So x approaches 3 of f of x. So let's go 3 minus. So that means x is less than 3, but not equal to 3, because there's no function value at 3. So this gets fairly technical, this sort of thing. Same calculation as before. And then the limit as x approaches 3 plus, which is where x is bigger than 3. This could be like x is 2.9, and this one might be 3.1. Think of it that way. Of f of x equals the limit as x approaches 3 from above of x plus 1, so that's equal to 4. So therefore, left and right limits are equal, and you write the limit as x approaches 3 of f of x is actually equal to 4. But just keep in mind that f of 3 doesn't exist because it's not defined. So the limit can exist even if the function is not defined at a point. And you can see why, it's just a hole. So if you go left and right, then you move closer and closer to that point from either side, it all goes to the same point at 4. So 4 is the limit. Does that make sense? Excuse me. Okay, this next one, let's look at the function first. This one is a function is x plus 1 when x is not equal to 3, and it's equal to 1 when x equals 3. So here, there was a hole in it again, but instead of not being, there's actually a value. When x equals 3, the function has a value at 1. So it has f of 3 equals 1 is the function value. So in this case, it's identical to the previous example. So again, I won't go into it again like we did before. The limit as x approaches 3 of f of x is equal to 4 again. But f of 3 is equal to 1. And so that means f of 3 does not equal the limit as x approaches 3. So it's not continuous there. That's a mathematical way of proving that. We already know it's not continuous. We can see it here. You can't draw that picture without lifting your pen off the paper. So there are 4 sort of basic examples that I wanted to cover and show you different aspects of it. And it's good to see them all together because there's some confusion about limits. Like for this number 2 one, it's so easy. Students get confused. They wonder, what do I do? Well, no, there's no problem. You just substitute. That's it. Full stop. So it's important to keep them in context. Let's have a look at this next one here. This one here. So with this one, if you substitute x equal to 3, so you try x equal to 3 to see if it works, and you end up with 3 squared minus 9 over 3 minus 3, which is 0 over 0. It doesn't exist. So it may be that it doesn't actually exist. However, sometimes you can do a little bit of algebra on this, and you can get rid of that problem point. And I can see here that I can factorize this. So this is what you can do sometimes, often in our school situation, but in practice, there are other ways of figuring this out. That'll cancel, because as x approaches 3 means that x is not actually equal to 3, so we can still cancel things. So that means it's the same as x approaches 3 of x plus 3. And where, of course, from the beginning, you saw here, there's a x minus 3 on the denominator, so x is not equal to 3 for this function. So that's the same thing as that line we had. That's just equal to 6. That is nothing more than a straight line, x plus 3. There's a hole in the function at the where we would go to 3. The answer is 6. That's the point 3, 6. That's the line y equals x plus 3. And that's all there is to that one. So that's just an example where you have a removable point, a problem point, x equals 3, because you get 0 on 0. But if you can cancel out that denominator with something on the numerator, then you can still get an answer. So that happens sometimes. Also another one. So this one is similar to the one we had before. Looking at the limit as x goes to 3, let's draw a picture. That's often the best way to do things. This one goes up to 3. We've got x plus 1 again. Of course, when up to equals 3, that says equals that one. And when x equals 3, that's 4. And when x is greater than 3, so you put 3 in that other one, you'll get 6. So it's going to be open circle there because it's a less than. And then that'll go up like this. So it looks like that. Let's put some dotted lines down to guide us there, just to give a helpful visually there. That's our function. From that, you can work out everything you like. clearly it's not continuous. The right limit is 6, the left limit is 4. The limits are not equal, so the limit doesn't exist. Simple, very simple. So let's work out on paper. As x approaches 3 from the left of f of x, this is where this notation is very important because it's a piecemeal function again. That's what we call it in Australia anyway. Piecemeal function, FN function. Now f of x in this case, if x approaches 3 from below, that means x is less than 3, right? So that means it's got to be this one. So it's x plus 1. So it's the limit as x approaches 3 for the low, it's x plus 1, so it's equal to 4. The right limit as x approaches 3 from above, so that means x is bigger than 3, of f of x is equal to, this time the function is greater than 3, so it's 2x. So that's equal to 2 times 3 is 6. The left and right limits are not equal. So that means that the limit of x approaches 3 of f of x does not exist. The left and right limits exist, but they're not equal. That's all there is to that one. I should put an arrow on this one here, and that covers that one. Does that make sense? And the last example, this is the y equals 1. This is similar to the hyperbola, except it's a square. So if I draw that, it'll look like this, asymptotic there, asymptotic there. That was a pretty bad asymptote. We'll try that again. That's better. Asymptotes have to look like asymptotes, I think. And that one there is also asymptotic. That was pretty not close enough. I'll try to make it a mirror image of the other one. It's an even function. Okay, that's good. So here, obviously you've got limits as x goes to infinity are both 0. But the limit as x approaches 0 from the left or right, let's have a look at that. If x approaches 0 from the right, you can see the function here, it goes to infinity. And if it approaches 0 from the left, it's also going to infinity. So that's really what it does there. So the limit as x approaches 0 from the plus, it doesn't exist. It's equal to plus infinity in a sense, but it doesn't exist. Because infinity doesn't exist. But you can say, for when you're drawing graphs and so on, as x approaches 0 from the plus side, y approaches positive infinity. And as x approaches 0 from the left, y also approaches positive infinity. That's perfectly legal to talk like that because we were talking about how to draw graphs, and that's all helpful. So there you have a nutshell on limits without getting too rigorous about it. Real limits has a lot more rigor in it, but this is like the high school version of it. You just more or less have to try and work things out, and that's what it's all about. We're not getting too technical about the limits. It took them a long time to get the right definition for limits, so we don't have, we're not going to do that. All right. Thanks, guys. I hope that was good. Let me leave any questions for me, or and I'll deal with those. Bye.